In this video, we will review the worksheet 1 homework assignment that I given you guys earlier this week that you turned in on Monday. All right, problem 1 says the table below depicts the world annual soybean production in millions of tons, and we have our year and our production. Part A said, could the data represent world soybean production as a linear or exponential function of time? Round to 3 decimal places if you use calculations to help you answer this question. All right, and so remember, if we want to determine if our function is a linear function, notice that our x values are our input values, right? We have world soybean production as a linear exponential function of time. So this is our time, and of course we have our production here. I'm going to call it P. And so our independent variable, our inputs are evenly spaced. If our outputs are evenly spaced, then we can say it's a linear function. Notice here, when I go from here to here, 161 to 170, that's a change of positive 9.3. From 1.73 to 180.2, that's a change of plus 9.9. And as you can see, I'm not adding the exact same thing each time. Here, that's a addition of 10.5. And so I can say, since those numbers aren't the same up to 3 decimal places like it says here, then I know that this is not a linear function. Okay? Now I want to check and see if it's an exponential function. And here I have to think about a constant percent rate of change being the rate of change, all right, a constant percent rate of change. And a percent rate of change, I have to do part over total or new over old. And so what I'll do here is from year to year, I'll take the successive year and I'll divide it by the previous year. And if that factor is the same for all years, then I can say that that is exponential, an exponential function, right? So if I do those and I run it to 3 decimal places, I get 1.05. And in fact, when I do all of the others, for instance, 180.2 divided by 170.3, I get the same value here up to 3 decimal places. And so since this is the case, I'm going to say that this function is an exponential function. Okay? Since it's an exponential function, I can write the function in the form P of t equals P naught times a to the t. And remember, we said that a is our exponential growth or decay factor. And since this is growing, these y values are getting bigger, or these p values here are getting bigger. I know that a is going to be a growth factor. And I'm spelling that wrong. It's a growth factor. All right. And this right here gives us, remember when we did that example in class where we started with P of 0, we started with P of 1, and we started with P of 2. And we ended up saying that this factor right here that we get every time, that is the thing that's going to be our growth or our decay factor. And so I already know that my A in this formula is going to be that 1.058. And so I would raise that to the t. And then my initial amount, we're writing this function in terms of t, which is the number of years since 2000. So my initial quantity is the quantity in the year of 2000, which is 161. So it'll equal 161 times 1.058 to the t. All right, so this factor here, remember, it always is your a in an exponential function. All right, and it's an approximation here because we have rounded to 3 decimal places, but that is fine. Another way that you can do that is if you didn't know that this 1.58 to the t was your growth rate, then what you can do is you can use your generic formula. We already know that the 161 is our P naught, but what I can do is I can choose some point. Let's say I choose the year 2002 and the production 180.2. Then I know for a fact that when I plug in 2 for T, then I'm going to get an output of 180.2. And I can solve this equation for A by dividing both sides by 161. and I'll get a squared equals this quantity here. I'll leave it here before putting it in my calculator. And then I can take the square root of both sides, and I'll get what a equals, which is approximately 1.058. All right, and so if you didn't want to remember that this thing right here is going to be your growth or your decay rate, then you can go through the process of solving. Notice if that was a 3, let's say I had a cubed, and I would take the cube root of both sides, or if it was a to the 4th, I would take the 4th root, so on and so forth. Let's go to parts C and D. All right, in part C, it says find the average rate of change. And remember, the average rate of change, well, we're using T here and P here. And so instead of saying F of X2, I'm going to say P of X2 minus P of X1 all over X2 minus X1. And if I want it to really be like completely mathy and completely, you know how math people are sometimes. Guess I shouldn't say that. But completely correct. I can say T of 2 minus P of T of 1 over T of 2 minus T of 1. And I can just plug these values in. Pick 2 points for... I don't just pick 2 points. I'm sorry. I'm specifically getting the average rate of change from 2002 to 2005, right? At 2000, T is the number of years since 2000, so that's T equals 0. So I'm going to say T1 equals 0, and then T2 equals 5. That means my formula is P of 5 minus P of 0 all over 5 minus 0. And of course, 5 represents 2005, the functional value in 2005, which is 213.5. So this would be 213.5 minus 0 corresponds to the year 2000, and the production amount is 161.0 all over 5, and that boils down to 10.5. The units here, remember, it's your numerator, which is millions of tons, and my denominator here is in years. So that 10.5 represents 10.5 millions of million tons. I'm just going to say million tons. It's the email. Million tons per year. And basically that's saying that between the year 2000 and 2005, I can use the word "in" there, but the average I'm going to say it a little differently, didn't I? World production and I am doing this. World soybean production increased, since it's positive, on average by 10.5 million tons each year. All right, and that will be our interpretation of that average rate of change. Parts E and F tell us to analyze this table looking at increasing and decreasing, or just the rate of change, and also the concavity, which is the rate of change of the rate of change, right? And so if I look at my table, in order for me to tell whether it's increasing or decreasing, all I have to do is look and see whether the output values or the Y values are getting bigger or getting smaller, right? And so when I go from one to the next in successive order, right, or consecutive order, they are getting bigger, right? Since that is the case, I'm going to say that is increasing. Okay? Just look at the table and see if it's getting bigger. If it is, it's increasing. If not, it's decreasing. When I think about concavity, I need to look at, okay, if it is already increasing, Is it increasing faster as I go along? If so, I'm going to say it's concave up. Or is it increasing slower as I go along, right? And this is when I can look at the differences in these numbers here. For instance, as I said before, this is an increase of about 9.3. Here, this is an increase of about 9.9. And then here, 10.5. And so as you can see, it's getting bigger and bigger every time I increase. And so the rate of change, if you think of these as the rate of change or like slopes or average rate of changes, these are getting bigger. And since that is getting bigger, then I'm going to say that is concave up. All right, and that's number one. Let's look at number two. It says the figure below shows the cost and revenue functions for a product. Label each of the following on the graph. And so A, I have fixed costs. B, I have break-even quantity. And then I have C and D. All right. The fixed cost comes from the intercept of the cost function. And my intercept, my y-intercept, I guess I can say my vertical intercept of my cost function, which is here. And so this point here represents my fixed cost. The break-even quantity, well, you remember when the point at which the revenue curve and the cost curve intersect is called your break-even point, right? And so that's my break-even point. And so if I want my break-even quantity, then all I have to do here is go to the coordinate on my horizontal axis. And this is my break-even quantity. I'm going to call it Q naught. Although it didn't ask for this, but if I were to go to the point on my vertical axis, I would get my break-even price or dollar amount. Part C, quantities for which the company is making a profit. All right, and so when we say making a profit, we mean to say that the profit is positive, for instance. All right, the profit is positive. So that pi function is greater than 0. All right, and this, since pi is the revenue minus the cost, is when the revenue is going to be greater than cost when our profit is greater than 0. And so all I have to do is look at which curve is on top, basically. And the curve that's on top, and I want to know when the revenue curve is actually on top here. And if I were to extend this, for instance, I would see that from Q naught to the end of my graph. So let's say our graphs continued here. These will be where our company will make a profit. And when revenue is smaller than cost, our cost is bigger, which is here in this area here. These are the quantity when we lose money. All right, and so I can shade my graph. It's these quantities where we lose money, and it's these quantities here where we make a profit. All right, that's problem 2. Problem 3 says label the figure, label the curves as the supply curve or the demand curve. Remember, with supply and demand, as price increases, if we see that as price increases, so does the actual quantity increase, then that's going to be our supply curve, because sellers want to supply more products at a higher price, right? High prices are in this area, are on the top of my graph. High quantities are to the right. And so if my graph goes to the top right, or ends there, then that's got to be my supply curve, all right? My demand curve, right? People want to buy more of a quantity when the price is very low, right? And so when the price is low, is at the bottom of my graph, given by this vertical axis, and it's a lot of quantities are at the right side of my graph, and so this would be my demand curve.